So today we're going to talk about the last section of C2 Part 1 for the AQA syllabus, which is all about the Haber process and the manufacture of fertilizers. Now, the Haber process is a vital process that produces ammonia, which is then used in lots and lots of other chemical processes. So it's really important that we understand it. Now, this is a triple science only topic, and particularly the stuff about the Haber process and the conditions in which it needs to take place, that is higher only triple. So if you are a combined science student, this is not necessarily for your exam. Additionally, if you have not yet got to grips with Le Chatelier's principle and dynamic equilibrium, I suggest you go back and look at previous videos or previous content that you've learned so that you make sure you're familiar with that, because you will need it for today. So first of all, let's look in general at what the Haber process is. So the Haber process is shown on the left here in this diagram. It's where we take nitrogen from the air and hydrogen from natural gas, and they are reacted with an ion catalyst under very specific conditions to produce ammonia, which is liquefied, which is condensed, and then taken out of your reaction system. Now, before we go into too much detail about what this process actually looks like and the conditions we do it, I wanted to first talk about why it's important, because one part of the content in this section is all about fertilizers, and it's very easily forgotten at the end of the topic. So ammonia is this compound circled in green here. It's NH3. And in this reaction, this reversible dynamic reaction, we make 2 molecules of nitrogen for every 1 molecule of 2 molecules of ammonia for every 1 molecule of nitrogen and 3 of hydrogen. But why ammonia? Well, ammonia is vital for the formation of fertilizers. And really importantly, because ammonia is a base or an alkali, when it's reacted with certain acids, it forms an ion called an ammonium ion, which is that NH4 plus ion. And that NH4 plus ion is really important in the manufacture of many fertilizers. Nitrogen is really important for plants because it's involved in the manufacture of proteins within a plant itself. So it's really useful. So let's first talk about fertilizers before we move on. So what is a fertilizer? Well, a fertilizer is a formulation. Remember, a formulation is a mixture that's designed to be useful, which is used to promote plant growth, and they're widely used. In fact, in the manufacture of food and in the industrial manufacture of plant products, fertilizers are routinely used. Now, fertilizers must be soluble, and that's really important what we're going to talk about later, because in order for them to be absorbed by the roots of plants, they must be dissolved in water. And mostly they contain ammonium, which is that NH4 plus ion, or phosphate ions, which is PO4 minus. And those 2 ions are really important for growth and development in a plant. Now, underneath here, I've given you a little table that just shows you some really common fertilizers and the essential elements that are found within them. So you have ammonium nitrate, ammonium sulfate, ammonium phosphate, and potassium nitrate. Now, think really carefully about how you might make something that has nitrate at the end or sulfate at the end. We've learnt about this before, and we've learnt about how you make certain salts when you react certain things with certain acids. So try and think to yourselves now what acids perhaps you might use in those manufactures. Now, one way that we can obtain materials for these processes is to start by mining raw materials. And one thing that we mine a lot of is something called phosphate rock. And I've got a picture for you there of a phosphate rock mine. Now, phosphate rock is not the only thing we mine. We also mine things like potassium sulfate and potassium chloride from the Earth's crust. And those things are soluble, so they can be used as they are if necessary. However, phosphate rock cannot be. Phosphate rock is insoluble, but it's very rich in phosphate. So it's important that we understand how to manipulate that phosphate rock to obtain compounds that we can use and that are soluble. And so underneath here, now this is something the exam board does expect you to know. They want you to know the reactions of phosphate rock with certain acids. So with nitric acid, with phosphate rock, you make calcium nitrate and phosphoric acid, which is then neutralized to make ammonium phosphate, which is a really useful fertilizer because it contains both nitrogen and phosphate ions, which gives you your your phosphorus, sorry. And when you react phosphate rock with sulfuric acid, you make something called a single superphosphate, which is a mixture of calcium sulfate and calcium phosphate. And finally, when you react phosphate rock with phosphoric acid, you make triple superphosphate, which is just a mix of calcium phosphate. And those are compounds that then can be used either directly as fertilizers or can be used to manufacture other fertilizers. So that's one way that we can obtain those materials. Now, the other thing that the exam board really wants you to be aware of is that fertilizers can be made in different ways. And what they talk mostly about is about comparing manufacturing methods. So if we talk, and I'm talking very briefly here, so if you need further detail, you can find that online. But if we talk about the manufacture of something like ammonium sulfate, okay, which you use sulfuric acid for, the industrial method to make ammonium sulfate, which is a fertilizer, and the laboratory method, and that's the method that you or I would use in the lab at school or in a smaller lab in order to make a sample, they differ quite greatly. They differ in different criteria as well. So first of all, in temperature. In the industrial methods, they'll be really specific about the temperatures they use, and they'll use temperatures up to about 450 degrees. However, in the lab method, lots of the neutralization process will just take place at room temperature. And then they will only use a Bunsen burner to evaporate water off at the end. So they're not using very high temperatures. And that makes sense because we don't have the capability to do that within the lab, with it being safe. In terms of equipment and process, if we look at the industrial method, there are massive and expensive plant machinery that is used to continuously produce ammonium sulfate. Whereas in the lab, we use versatile equipment that we can use for lots of different practical experiments, and we do a batch process. We make one batch at a time, mainly because we are investigating it rather than using it on an industrial scale. The starting materials in the industrial method, they can use raw materials. They'll use the air, they'll use raw sulfate, they'll use water that is being fed in. Whereas in the lab, we are much more likely to use reactants from a chemical supplier rather than manufacturing our starting materials ourselves. Huge quantities are made in the industrial method and very, very quickly. But in the lab method, obviously, it's smaller and they are made more slowly. The running costs in the industrial method, whilst there will be very expensive startup costs, the long-term running costs are lower because all of the automatic mechanisms and machinery reduces labour costs. And labour costs refer to how much you have to pay somebody to do these things. So you're not having a person doing each of these steps. You might have a person overseeing a very large-scale manufacture rather than having many people doing individual steps. However, if you were going to make ammonium sulfate or other fertilizers in the laboratory method, it's a very labor intensive method because you have no automation. There is no automatic routine set up using machinery. So your running costs would be very, very high. So those are the bits of information that you need about about fertilizers and about manufacture of fertilizers. It doesn't look like a lot, but it is something that people may forget to revise. Just make sure you have it and you have made yourself aware of it for your revision. Let's go back to the Haber process now, because this is the part that is triple science only, but also higher tier only. So on your screen, you can see the reversible reaction that is the manufacture of ammonia, the Haber process. You have nitrogen reacting with hydrogen to form ammonia. You can see that there are 4 molecules of reactants reacting with 2 molecules of products. And I would always just have a little look at that when you start answering questions, just so you've got it in your head. If you see a reversible reaction sign, you know they might be asking you questions about equilibrium. And then you're going to need to know about exothermic, endothermic, and about number of molecules. I've also added on here too for you that this is an exothermic reaction in the forward direction. Now, in the exam, they will either explicitly say that or they'll give you a value of kilojoules per mole at the end. Now, any value that is negative shows you an exothermic reaction. And that's because energy is released as the process of the reaction happens. So the products actually have less energy than the starting materials, hence why you get a negative energy change. And that's actually known as your enthalpy change. So that's the reaction. Now, the conditions that this is done in industry are as follows. The temperature is at 450 degrees Celsius. The pressure is at 200 atmospheres. And when we say 200 atmospheres, what we're basically saying is 200 times atmospheric pressure. 1 atmosphere is the pressure of the atmosphere around us as we stand. So 200 atmospheres. And lastly, we use a catalyst of iron. Now, what you need to be aware of is why we use these conditions. Now, first of all, I'm going to show you a graph. And this graph is quite a common graph to see on an exam question. Here you've got a graph that shows yield of ammonia along one side on your y-axis and pressure in atmospheres at the bottom. And as you can see, more pressure gives you a higher yield. And we'll talk about why that is in a minute. But what I want to focus on is this here, the temperatures. You can see different curves for the different temperatures. Your steepest curve up here is your lowest temperature, 350 degrees, and your most shallow curve down here is 550 degrees. Now, what this shows us here is that the best yield of ammonia comes from a low temperature. Now, why is that? Well, that's due to the fact that we have got an exothermic forward direction. And we know that when you increase temperature, it will always push the equilibrium toward the direction that is endothermic. And our endothermic direction is actually backwards. So by having a high temperature, what we do is we actually reduce the yield of ammonia because we make more nitrogen and hydrogen, which is really not ideal. But you can see here that we use 450 degrees and not 350 or even lower, because actually a lower temperature, perhaps of 200 degrees, would give us an even better yield of ammonia. But why do we use 450 degrees? Well, the answer is it's a compromise. The lower the temperature, the slower the rate of your reaction. And if the reaction is too slow, well, then the reaction is no longer cost effective. You're not having as fast a reaction to produce as much product as you would need to. So therefore, a temperature is selected to be a compromise between yield and rate. So we use 450 because any higher would dramatically reduce the yield, and any lower would give us too slow a rate of reaction. Now, next we want to talk about pressure. And pressure here is at 200 atmospheres. And you can see on the graph down here that actually having the pressure around 400 would be even better. Now let's first of all look at why we use a higher pressure. Well, over this side we have got 1, 2, 3, 4 molecules, and over this side we've only got the 2, and we can see that from the big number. Now, as we know, when you increase pressure in a reaction, it favours the direction with the fewest moles, and so it pushes the equilibrium to the right in the forward direction, which means we have a higher yield of ammonia, which is great. So an increased pressure will give us a higher yield of ammonia. But why do we stop at 200? Why do we not bang it all the way up to 400 if we're going to get even higher yields? Well, the reason for this is that at high pressure comes high cost. When you are reacting things at very high pressures, not only do you have to have a safety consideration because the risks are obviously a lot higher, but you have to have specially designed equipment that can withstand those pressures. And with the higher level of specialism in the equipment comes much higher costs. Also, in order to exert pressure that high, you need a lot of energy to do that as well. And so therefore, it's really not very cost effective to use very high pressures. And lastly, we use a catalyst. Now, catalysts increase the rate of a reaction by lowering the activation energy by providing an alternative reaction pathway. They do not affect the position of equilibrium. And what that means is it does not affect the yield of ammonia. The yield will be the same with or without a catalyst. The catalyst just makes sure that we get there more quickly. So the iron catalyst is simply there to reduce the activation energy by providing an alternative reaction pathway. So that's everything you need to know now for the very end of C2 part 1, I should say. Sorry, I got a bit ahead of myself. Now, as always, what we need to do is make sure we've looked at our tick list and we feel comfortable that we understand that. And then we want to go and have a look at this question. So this is one example of a past paper question. It is a 5-mark question. And the figure 2 that they refer to is a graph very similar to this one here. Okay, it's just a graph showing us different temperatures and pressures and how they would give us different yields. And they say, Use figure 2 to suggest and explain why the conditions used to produce ammonia in the Haber process are a temperature of 450 degrees and a pressure of 200 atmospheres. So what you need to understand and explain is, why do we use 450 and 200? Why not higher? Why not lower? And particularly try and think about this idea of compromise between yield and rate. Now, it's a 5-mark question, so you will need a good 5 minutes to answer it. I want you to pause the video now and have a go at this question. So you should now have had a go at the question. If you haven't, please do make sure you have a go. It's really important that you test yourself in order to fully understand it. So let's look at the mark scheme together then. So the first point in this mark scheme you might be a bit confused by. It says the reaction is reversible. Now let me be clear. You're not necessarily going to need to write very brutally the reaction is reversible at the beginning, because I can appreciate how you might look at that question and say, well, how does that make sense? How is that a natural start? But if you look at what they accept, which is what this bit is in italics underneath, allow stated as equilibrium or forward backward reaction anywhere in the answer. So if you refer to equilibrium or forward or backward reactions, maybe when you're explaining about why the forward reaction would lower the yield of ammonia, or anything later on, then you will get that mark. So that's a mark that's just going to be there. It's just the idea that you understand that this is an equilibrium question. So now we want to talk about temperature first. So the forward reaction is exothermic. So increasing the temperature lowers the yield of ammonia. Now, that's the explanation for why we want a lower temperature, okay? And you could obviously go further there and explain that that's because when you increase temperature, it favors the endothermic direction. And then that second bit there is the compromise bit. But a lower temperature is going to decrease the rate of reaction, hence why we go to 450, as it is a compromise between yield and rate. A higher pressure would increase the yield of ammonia because the forward reaction produces the least number of molecules or moles. Now, it's important, guys, as I've said before, molecules and moles, both appropriate words to use. Particles will sometimes get you the mark, atoms will not. So be very clear in your language. However, although using a very high pressure is going to give us our best yield because of what we've just explained, higher pressures would involve a higher cost and energy output. So therefore, we tend not to use any higher than the 200. Now, here it talks about ignoring risk and explosion. Okay, the reason for that is the idea of this high cost is to create equipment that protects us. There is more risk with higher pressures, but we're talking about an industrial process here. So really that comes within the idea of high cost and energy output. So that is the Haber process and fertilizers. Feel free to watch this video again if you need to go back over things. And then we're going to move on to organic chemistry in our next video.